So in today's video, we're going to be talking about graph traversal and more importantly, something called BFS and DFS. So before we get started, let's review something called graphs. So let's recall what a graph is. And on the right, I have a picture of an example of a graph. So what exactly is a graph? Well, it's basically a collection of vertices or nodes, as well as edges which connect the vertices together. Now, this basically shows the relationship between the objects or the vertices slash nodes. And a really easy way that you can think about this is just circles connected by lines. Okay, so now let's talk about graph traversal since we just reviewed graphs. Well, basically, graph traversal is a complete search of a connected portion of the graph. And essentially, it's a very important operation on graphs. So on sets, we might add two sets together. On graphs, we like to traverse them. Now, a few examples that we've seen on the CCC or any competition really are the following. So we've seen Maze in 2008 S3, Nighthop 2010 J5, CoinGame 2012 S3, and then there's also Escape Room 2020 S2. So you can see that there's a lot of examples of graph traversal questions, and we're going to be discussing a few of them. All right, so graph traversal, what's the general idea behind it? Well, the general idea is that the search can begin at any single one of the nodes. Because remember, we're looking at a graph. Graph traversal is defined as looking at all the nodes in a portion of a graph, right? So we can begin our search at any one of the nodes. And essentially, all nodes connected to a starting node will be visited, so that portion of our graph. Now, basically, once visited, a node will be marked as visited so that it won't be visited again. So once we process that node, whatever we want to do with it, we don't want to visit that ever again, because otherwise there might be some infinite loops going on. And the way we do that is we basically create a Boolean array called visited, where basically vis nd means that nd is visited. So nd is node. And basically the visiting order varies depending on the method that we use, and that's exactly what we're going to be talking about in today's video. So graph traversals, let's talk about neighbors. During any graph search, we must iterate through all neighboring nodes of our current node. What does that mean? Basically, when we're at a current position, say we're at one of the cities, we're going to expand out and look at all the adjacent cities that we're close to. So all the neighboring cities. So for example, in an edge list, we're going to go through all the edges and we're going to check if the current edge contains the current node, because that's what an edge list is defined with. For an adjacency matrix, we're going to iterate from I is equal to 1 all the way to n, and basically check if adj cur I is true or not. And then finally, for an adjacency list, we're going to iterate through the list associated with the current node. So adj cur, for example, is going to be a list of all the nodes it's adjacent to. And typically, we're going to be using adjacency lists, but the other implementations do work as well. All right, so there are two main ways to traverse a graph, and these two ways are basically breadth-first search, also known as BFS, and depth-first search, which is known as DFS. And these are the main two algorithms that we're going to look in this video for graph traversals. There's a bunch of other ones, but these are the most fundamental and basic ones. All right, let's start off with breadth-first search. So BFS essentially encapsulates this idea. So it visits nodes depending on the distance from the root. The root is whatever you want it to be. So it could be any starting node that you want. It's going to visit the nodes based on the distance of it. Another way you can kind of think about this is the closer the node is, the sooner it's going to be processed. So it's a layer by layer approach, and you can kind of think about it as radially expanding out or going down a layer of the tree. So the way we kind of motivate this to get that layer by layer style is we use something called a queue to store the nodes to visit. And in the implementation, we're going to see exactly how this is used. Now, another application of BFS is that because it's based on the distance from the root, we can actually use this to calculate the distance or the number of edges needed to go from a starting node to any other node based in that portion of the graph. All right, so here's a diagram of what exactly BFS does. And in this case, red signifies that the node has been visited and processed. So you can see that we're starting at node number 1 here, and the green ones are the adjacent nodes that we want to visit. So once we process the red node, we're going to visit the green nodes, and let's see what happens. Well, the green nodes have just been processed, and now their neighbors are going to be processed next. So 5, 6, 7 are going to be processed. Then their neighbors are going to be processed as well. Now remember, it's the direct neighbors, not any of the leading neighbors, right? Second degree neighbors, for example. So you can see 8, 9, 10, and 11 are going to be processed. They have been processed, and now their neighbors are going to be processed. And once we're done the graph, there's no more items in the queue or any nodes to be processed, so we're done our breadth-first search traversal algorithm. So here's some pseudocode for how to implement BFS and the algorithm. Notice that we use a queue at the front. Next, we push in our starting node, mark the starting node as visited. We can use, once again, a Boolean visited array. We're going to say, while the queue is not empty, take out the current node from the top of the list or the front of the list. And then basically, for each of the n nodes adjacent to cur, if it's not been visited, then mark it as visited and then push it into our queue. And this kind of style allows for the layer by layer approach. Now let's see what we want to do if we wanted to add some distance to this. Say I wanted to say, what is the distance from my starting node to any other node in that portion of the graph? I can easily do it like so. So notice that distance start is equal to 0, and all I've modified is saying that distance n is equal to distance cur plus 1. And that makes sense, because it's going to basically say that the distance to the adjacent node that I just went to, that I'm going to, sorry, is equal to the distance of the current node that I was at plus 1, right? And that makes sense. So that's the little thing that you need to add for the distance. Next, let's talk about depth-first search, also known as DFS. The basic idea of DFS is that it explores each branch to its furthest before backtracking. And the way we do this is we use recursion, or a stack, to implement DFS. So notice on the left, this is basically a stack trace of what's happening with our DFS. If you look on the left and follow down the arrows, it's going all the way down, comes back up a little, goes down the right branch, comes back a little, all the way to the root, goes down to the right, and then comes back up. So this one is a little less intuitive because it's recursive, but it's also a very powerful algorithm if we wanted to bring some stuff up in our graph, for example. So notice that we're going all the way down. You might want to bring some information back up into our graph so that later on we could use it. So this is basically the DFS diagram. So green signifies the travel path, and remember that it goes all the way down. Now, you might be wondering, what is the order that it goes down? Well, actually, it's arbitrary, and it's really dependent on the input of your graph. So for example, in this one, 2 might be adjacent to 1 because it was inputted earlier in our problem. So in this case, this is the travel path, and white signifies that the node has not been visited. So you can see that they have been marked as visited. So it'll go 1, 2, 3, then comes back from 3 to 2, and then processes all the nodes that are adjacent to 2. So red signifies that the node has been pushed into the stack. And now you can see that the next travel path is this green section here. So it goes 4, 5, 6, 7, and then it's going to mark it as visited. And what's going to happen? Well, it's going to go 4, 5, 6, 7, comes back to 7, 6, 5, 5 sees that there's an adjacent neighbor, so it'll go 8, 9, 10. It's going to come back up, and it's going to go to 4, because remember, our travel path was 1, 2, 3, 3 to 2, 2 to 4, 4, 5, 6, 7. Then it went all the way down, came back up a little, and now we're going back to 4. So now that we're at 4, we go down the travel path, mark those nodes as visited and process them, and then finally we visit these last 2 nodes, 15 and 16. And there we go. So that's pretty much the travel path of DFS. It's a little unintuitive at first, but once you understand the applications, it's really, really important. So here's some pseudocode of DFS using a stack. You can see that it's very similar to the BFS code, but instead of a queue, we're using a stack to maintain that idea of keep on going down, right? So remember, a stack is first in, last out. Now you might be saying, well, look at this code right here, recursive. It's actually much shorter than the stack implementation because basically recursion is in it itself already an implementation of a stack pretty much. Okay, so let's talk about BFS and DFS on not so obvious graphs. So for example, we might say some problems require BFS or DFS even though there's not an obvious graph. So basically, BFS or DFS can be done on grids, for example, where we can see Nighthawk and Maze are pretty solid examples of those two kind of applications of BFS or DFS on grids. And we also have BFS or DFS on states. And what does a state mean? Well, basically in CoinGame, a state could mean the positions of our current coins. And so you can see that BFS is just an idea. BFS and DFS are just ideas. They can be used on graphs, grids, or even states. All right, so let's talk about graph search on grids. So graph search on grids basically follows as such. Each cell is basically a node, and movement to adjacent cells are basically edges. So think about a square and then it's adjacent to 4 other squares as well. Or in this case, 8, but let's say you can only move up, down, left, right. Well, basically, the movements are the edges. The valid moves are the edges. And so what you'll do is keep an array of possible moves so that they can be easily iterated through. This is something that we're going to see in examples of later on in CCC problems. But for now, just remember that we can store the moves that we can do and easily just iterate through them. And basically what you have to do is you must check if the cell is within the current range of the entire grid. Because what you'll do is, say you're on the edge of the graph. If you try to move to the left, it won't work. And so for that reason, if for zero index graphs, we want to check whether or not the current row that we're going to go to is basically within the range of the bounds. So row and column as well. All right, so let's talk about graph search on states. This is pretty straightforward as well, very similar to graphs. Basically, each state is a node, and each possible transition to another state is an edge. And basically what we can do is we can use a string or an integer as a representation of a state, and we must use a data structure such as a set to keep track of the visited or not visited nodes. We can use a set, a hash map, whatever, as long as we can easily index and say that this node has already been visited. All right. And finally, we must be able to convert the state into an integer or a string very easily. And we must convert this integer or string if the queue, stack, or recursive method uses integer or string. So that basically just means we need to have an implementation, a solid implementation of our state. All right, so that was a lot of knowledge just from BFS and DFS. And let's cool it off by doing a bit of comparison between them. So for BFS, basically it visits nodes in order from edge distance from the node that we're starting off at. And the true distance is only accurate if the graph is unweighted, because we're doing +1, right? And so if we're doing layer by layer approach, we can obviously see that the distance is true. Although it's longer code and slightly slower, It uses more memory. These are some of the draw-offs of BFS. But that distance, if we really need that distance, then we're going to definitely need BFS. Now for DFS, it basically explores branches as far as possible before backtracking. And the problem with it is that it does not get distance between start node and any other node. But the upside to this is that it's shorter code, has a faster runtime, just slightly, okay, just slightly, and uses less memory. All right, so just as an exercise for you to try out, given a connected, undirected, unweighted graph with n nodes labeled 1 to n, print the distance from each node to node 1. So you can see here in the sample, I've given all the edges, 1, 2, 1, 3, 1, 4, 2 to 3, 2 to 5, 3 to 7, 5 to 6, 6 to 7, 6 to 8. And the distances from 1 to 1 is 0, 1 to 2 is 1, 1 to 3 is 1, 1 to 4 is 1, 1 to 5 is 2, 1 to 6 is 3, 1 to 7 is 2, and 1 to 8 is 3. So try it out. Try this example here. If you can get it, that's awesome. And my final example for BFS or DFS on grids is basically given a 2D array of ones and zeros with 0 representing a floor and 1 representing a wall, print if it is possible to go from the top left corner to the bottom right corner. And basically these walls are going to block you. So in the first example we can see here, can we get from the left to the bottom right? Well, yes, we can. We can just follow that S or that 2 kind of pattern, kind of S snake pattern, go from the left to the right. In the second example, we can see it's possible. We just go straight down and then to the right. And then finally, for the last example, you can see that it's impossible. And the reason it's impossible because we can only go up, down, left, right. So at the second bottom right 0, we can't get from there to the bottom right. And so that's pretty much it for BFS, DFS, and graph traversal.